Great. So we're going to continue with, what section is this? 13.7. So let's review where we are. F of x, y, z equals some scalar function. Then we can talk about the surface integral. It's sometimes referred to as a scalar field. Surface integral over the scalar field F. With respect to the surface S is given by, how could we write that into? So there are two cases. Okay, so suppose S is parameterized by R of UV versus S is given by, let's say, some function z equals g of xy. How would you define the scalar field, the surface integral over the scalar field in this situation? What do you mean cross product?
You take the cross product and multiply with the function.
So
The function times the magnitude of the cross product, which is the normal dA.
So double integral over S of
RUV.
Of F.
F of RUV, meaning you plug in the parameterization into the function you're integrating,
and the cross product of the normal vector
times the magnitude of the normal. So it's the magnitude of RU cross R. dA. Which you can think of this as being over D, where it's the projected region. What would it look like over here? It's going to be a double integral.
F of x, y, and g of x.
X, y, and you replace g with whatever its function is, and?
Times square root of f of x squared plus.
Square root. Well, in this case, it's partial of g with respect to x squared plus partial of g with respect to y squared plus 1. By the way, that was the answer to the first two questions on the quiz, I believe. So in this case, if you know your parameterized, your normal vector is given by that expression, the cross product of the partials, and if your surface is given by some equation, some scalar equation where you can actually solve for one of the variables in terms of the other two, then your normal vector is given by minus the partial with respect to x, comma, minus the partial with respect to y, comma, 1. And that can be permuted with respect to the variables. And so let's actually do, so we actually computed one of these integrals in the last class. I have another example I want to go through, but let's also just throw onto that the example from the quiz, problem 5. So that's the definition. It was basically, we could use that to compute a generalization of volume where we don't have to project into the coordinate planes, we can project onto a surface and find the volume hovering above that surface. Well, let's move to another example where it's quiz 7, problem 5. I'm doing version A. Let's see what this is. So it says to compute the double integral over S of y ds. And S is a paraboloid y equals x squared plus z squared inside, that lies inside the cylinder plus z squared equals 1. Okay, tell me how you go about that.
Can you choose that n is going to be, you choose the y, so it's going to be x, f,
First you find your n, which is going to be
Yeah.
what?
so it's going to be
Negative
2x,
Negative 2x.
negative 2x,
1,
1,
negative
and
2z.
negative 2z.
Yep, that's using the formula. And so, what do we need to find after that?
Magnitude?
We need the magnitude of that. So that's just going to be the square root of 4x squared plus z squared plus 1. Then what? This is a z.
You have to plug in y into.
What do you mean parameterize?
In terms of cosine and t.
Why would we do that if this is what we're doing?
You plug x squared plus y squared into the double integral.
Okay, what's actually going on here? Explain to me how this helps us.
It gives limits.
It gives limits. How? What's going on?
Well, I mean, x and z are only going to go between 0 and 1. Or negative 1 to 1, right? No, it would be 0 and 1.
Not exactly. What does our region look like? You can't just say x and z go between 0 and 1, because that defines a rectangle. So you have a
Isn't it a
rectangle.
circle?
It is a circle, but how does it look? First of all, what does this guy look like? It's a paraboloid. Where is it? Oh, it's a paraboloid. You guys know. What would it look like?
Along the y, along either along the
It's
y.
running along the y, so it's opening that way along the positive y. So we have this paraboloid opening up that way.
Cuts off at 1.
And it cuts off based on how this cylinder is projected. So that projection is your region of projection. So you're really here looking at this circle in the xz plane. That's your x and that's your z, that's your y. Okay, so it's projected down to that circle. So what does that tell me? So now the surface integral over S, it's going to be the double integral over D, where D is this guy, of what?
Of y.
Of y. So what do I write down?
X squared plus z squared.
You have to replace it with the variables that you're projecting into. So my y is actually x squared plus z squared. So the y is this, I put that in, times the magnitude of the normal, which is this. dA, now tell me how to set up these limits. What would you do?
It's just r d theta.
Yeah, you do polar coordinates, right? The fact that it's an x and a z doesn't make a difference if it were x and y. So I just let x, think of x as the r cosine theta, z as the r sine theta. Sort of do a polar coordinates kind of setup. So this guy would become r squared, this would become 4r squared plus 1, and dA would become r d theta. Give me the limits.
0 to
0 to
1,
1,
and then
So 0 to 1, that's the radius of the circle.
and then
And then
0
0
to 2 pi.
0 to 2 pi, so that's the angle subtended by the circle, it's a full circle. So that would have been the answer. It's kind of annoying to figure out, but a new sub does it.
all of them.
But that I think I put that in the bonus. Not because I think it was an unfair question, but I think it would probably be kind of tedious to work out. Semi-tedious, I don't know. But if you wanted to go, but that was the answer, the last answer to the quiz. And if you want to evaluate that, how do you do it? I'd probably do something like, just do a substitution. Well, for one, there are no thetas, so really I know I'm going to have 2 pi times this integral. Well, that would be r cubed now. dr. So that's what I would end up having. And at this point, I would just do a u substitution. I'm like u squared equals 4r squared plus 1. Right? Notice that my r cubed I can think of as, let's leave that as r squared times r. And so now I get 1 over 4u du is equal to r dr. And my r squared, I can solve for the r squared part from this. So that's just going to be u squared minus 1 over 4 is my r squared. And so now just plugging that in. So give me 2 pi times 1 over 4 times the integral of r squared would become u squared minus 1 divided by 4 times this guy, which is just u, times r dr, which just becomes u du. And I probably changed the limits there as well, but essentially now we'd have something like pi over 8 times integral e to the 4th minus u squared du. And when my r is 0, my u is just 1. And when my r is 1, my u is what?
5.
Well, radical 5. So that's my integral. And so u to the 5th over 5 minus u cubed over 3 between 1 and radical 5. Radical 5 to the 5th over 5 minus radical 5 cubed over 3 minus a 5th plus a 3rd. Yes.
Question, since you're integrating over the area of the circle, can you just multiply by pi r squared of your circle?
No? Why can't we do that?
That's what, I don't know.
Did you guys hear his question? He said we're integrating over a circle. Why didn't we just do the pi r squared trick?
So right here you don't have a constant.
You need a constant to do that
You
trick.
need a
That's why.
constant. to
So
do that, so.
that's because when we're thinking of the definition of area, remember what that definition was. It was just a constant, right? So we know that the area of D is actually the double integral of 1 dA, right? So if you have a constant, so if you have the double integral over D of any constant dA, this is just a constant times the area. Right? That doesn't work in this case because we weren't integrating a constant. So we actually weren't finding an area, we were finding a volume. And so the function, because it was a non-constant function, that made the answer the difference. Okay, so you can't do that trick unless you have if you're integrating double integral of a constant. You can think of that purely in terms of area. And so if your D is a circle, this literally gives you pi r squared in any case. Okay, so that's what we have. Let's do another example. The rest of the bonus problems we're actually going to do today. After this example, we'll start doing that. Another example, computing a surface integral over a scalar field. The double integral of x plus z ds, where s is given by, let's say, a parameterization. R of x comma theta equals x, 3 cosine theta, 3 sine theta. Where my x goes between 0 and 4, so these limits are given. My theta goes between 0 and pi over 2. What kind of surface is this? It's a quarter cylinder. What's the axis? It's running along the x-axis. So it's a quarter cylinder running along the x-axis, just the skin of the cylinder, the rounded part. Okay. So if you wanted to draw this guy, so x goes between 0 and 4, so it's over here, and it's running along here. Right, but you can just imagine this as the outer part of a cylinder that's in general, but we only take the part where the theta is between 0 and pi over 2. Okay, so that's our surface S here. Okay. What do we do? Find a normal vector. Okay, how do we do that here?
Take the cross product of the
Alright, since the parameterization is given to me, I'll probably just jump right into the cross product. So I'll take the partial with respect to x of this, and what would I get? 1, 0, 0. And I'm going to cross product that with the partial with respect to theta. Negative 3 sine, 3 cosine. Right, and set that up in your IJK formula. What would I get here? I would get 0, 0, 0 minus 0. In the middle, I would get 3 cosine, and then I change the middle sign, so it's minus 3 cosine theta. Although here the signs aren't going to matter because we're going to take magnitudes afterwards, but let's just keep ourselves honest here. And then in the k, this is minus 3 sine theta minus 0. So that's your normal vector. You need to find the magnitude of this normal vector. That's just going to be basically square root of 9, right? 3. And so now we just start plugging in. So we're going to plug in the parameterization into this function. So x is literally itself. My z coordinate is given by 3 sine. So I'm going to plug those in. So it's x plus 3 sine theta. That's what I'm integrating. ds is the magnitude of the normal vector. dA, but we actually know dA here. They gave us the limits directly. Let me put dx d theta first. Although in this case it doesn't matter because they're going between constants. So this is 0 to 4, 0 to pi over 2. And so that would be the setup. And then from there it's just evaluating that integral. We're fine evaluating. Do I have to? You guys want me to go through it? Yeah.
Since two of the limits are constant, can't you do one and do the another one and multiply the results together?
No, because it's not multiplied, they're being added.
Oh, okay.
If it was x times sine, then yes, I could literally integrate the x's and integrate the thetas and
Okay, oh,
multiply
yeah.
it together. But here they're being added, so
Added.
we have to sort of go through the whole thing. Since you asked, let's just quickly do it. So we'll just do 3x plus 9 sine theta, dx d theta. Integrate this, we would get 3x squared over 2 plus 9x sine theta between 0 and 4. Plug in x equals 4, what do we get? 4 squared is 16, divided by 2 is 8, 3 times 8 is 24, plus 9 times 4. 36 sine theta. If I plug in x equals 0, everyone dies, so that's it. And so now I integrate that with respect to theta. So this is 24 theta. Integral of 36 sine theta is what? Minus 36 cosine theta. Between 0 and pi over 2. So that gives us 12 pi. What's cosine of pi over 2? 0. And minus 0 plus cosine of 0 is 1, so that's 36. What you can think of that as, remember that curved cylinder that we had? If we projected a surface above that, which is given by S, we just calculated the volume of that surface that's perpendicularly projected onto that side of the cylinder. That's a geometrical interpretation. We're never going to interpret it that way, but that's what it is. We're actually going to have an application for scalar fields pretty soon. Okay? They're very important in the next few fundamental theorems that we're going to cover.
Okay.
Yes?
A question. Since you have you are calculating the volume, but why use dA? You said we are calculating the volume, what is 3-dimensional, but you use the dA. And
Yeah, but that does give you volume. If you take the double integral of a function, dA, it gives you the volume under the function, the net volume. That's what it is. Remember, like a single integral gives you area, right, where area is 2-dimensional. In the same way, a double integral will give you volume in general. It's just that if you have a constant, that means your function has height 1. If your function has height 1, then volume and area are the same magnitude. That's why you can look at it that way. But double integrals of an arbitrary function computes the net volume under the function. Okay. Here's another important idea. How to orient a surface. We know how to orient curves. Let's talk about orienting surfaces. So again, this is by convention, but there is some method to the madness here, so we'll discuss the convention of orienting surfaces. Now, back when we were in 2D, let's remind ourselves, let's make sure we know how was orientation done in 2D? It sort of meant like direction. Right, so you can have a curve going this way, that's one orientation, whereas the same curve going that way, we call this the negative orientation. So this is an orientation. This is the negative of the above. But there was a situation where we described something being negatively oriented or positively oriented in general. What was that? And what did that apply to? Guys, remember when we used that language? What sort of situation? Yeah.
Oh wait, so positive orient is sort of like if you like wrap your hand around the curve and your thumb points away from the page, or counterclockwise.
Counterclockwise orientation. When you talk about positive orientation or negative orientation in general, it applies. It's a characterization of closed curves. Positive means you're traveling around this guy in a counterclockwise fashion, counterclockwise. Whereas negative means you're traveling around in a clockwise fashion. Right? And that's what positive and negative. And yes, as you suggest, the method behind the madness is because that follows the right-hand rule. Right? So it's very useful in determining the direction of a cross product as well as determining the directions of electric fields and all sorts of nice applications to that. So they kind of made the orientation to sort of fit nicely in with some physical properties that we have. So that was for curves. So these are all flat in 2D, but how do you orient a surface in 3D or higher dimensions? You don't really orient it by looking at things like going about the direction around the curve. You oriented them with normal vectors to orient the surface. We use normal vectors. So, for example, I can have this surface hovering in space, a flat sheet here. And I can describe my normals. I can use a formula to get the normals such that they all point up, for example. So at every point, I can calculate a normal vector in such a way that the z coordinate is always positive. And I could say, for example, this is oriented upwards. Right? Similarly, how I can say this is oriented to the right, its negative orientation is moving to the left. I can orient in 3 spaces up or down or right or left or something like that. But the normal vectors themselves determine that. And I can take the same surface, but I can instead take the negatives of all these vectors so that the z coordinates all point down. And I can call that oriented downwards. But again, there's a notion of for a closed surface, similarly to how we can have closed and open. Those sort of things are going to be important. So I'm going to define for you a closed surface very intuitively. I'm not really going to give a strict mathematical definition of it. We say S is a closed surface if it is the boundary of a solid object. There are some definitions that say something like a surface is closed if it splits space into 2 parts where in order to travel from one part to the other part you have to travel through the surface. But by that definition a plane is technically a closed surface and I don't really want to admit that definition. But that would be a more rigorous definition. Here, just imagine some solid object and just look at the skin of that object. You have a closed surface, right? No gaps, no holes, it's literally the entire boundary of a solid object. We think of that, we call that a closed surface. Okay? And it turns out we can induce a positive or negative orientation on such a surface. So let me define that. We say a closed surface is positively oriented Now the language here is very important. I know it's kind of a definition in words, but the words are important. If its normal vectors point, does anyone know? Huh?
Outwards?
Outwards. Now the word outwards is very important. In particular, I didn't say it points up or down. Outwards can literally mean either one of those. So positively, a surface is positively oriented if our formulas that we use for its normal vectors force all the normal vectors to point outwards. For example, I can have a sphere and I can talk about its normals pointing outside, or the sphere, that's positively oriented. Or as for example, in the bonus for the quiz, I said let S be the boundary of the region bounded by the paraboloid z equals x squared plus y squared and the plane z equals 1. So this was from the quiz, the paraboloid does this, and then the plane z equals 1 is just a flat thing cutting it off. The outward orientation to that would be on the top, the normals point up, but on the bottom, the normals point down. And that was positive oriented. Yeah.
If it's like z equals like the root of x squared plus y squared, that's a cone, right?
It was a cone.
Okay.
So this was z equals x squared plus y squared and z equals 1. Intersect those two surfaces and find the boundary of the volume they trap, and you would get this. I think the other version was I put the square root of this and z equals 1.
I think it still said paraboloid, so I thought you were trying to like trick me.
No, that's just a typo. Right, so that one would be that. And again, positive oriented means you were supposed to draw a bunch of arrows. You can draw one on each part of the surface. But the important thing was they were pointing out of the surface. And this defines the positive orientation. Conversely, so negative orientation is obviously the other way around. So can do these three examples again. Just stay negatively oriented. So I can have a sphere that's negatively oriented. Literally all normal vectors would point inwards towards the center of the sphere. So I can, if I have something like this, vectors on the top surface would point down, vectors on the bottom surface would point up, they would point inside the object. If I have a cone, vectors on this side will point up, vectors on the top would point inside the object. So there are many theorems. There are theorems that I'm going to tell you that require our closed surface to be positively oriented, and that just means normal vectors point outwards, and you need to know what that means. It doesn't mean up or down, because you can have things pointing up and down if you split the surface into parts. Right? Similarly with a sphere, some of these point up, some of them point down. You just need to know for the situation you're dealing with, you need to be able to watch the right coordinate, make sure it's positive or negative as required. Right? And the easiest way to figure that out is, well, draw the surface and you'll be able to see, okay, if I'm looking at the roof of this thing, I should make sure my normal vectors are pointing up, so the z coordinate has to be positive. If I'm looking at the curved part of this thing, all my normal vectors need to point down. I need to make sure the z coordinate is negative. Right? So if I'm using the formula here, for example, here I would use minus partial respect to f, minus partial respect to y, positive 1. Whereas down here, I would use the partial respect to x, partial respect to y, negative 1. Where on the top, my f is equal to the function 1, while on the bottom, my f is equal to x squared plus y squared. Right? So it's going to take that sort of dissection.
So, wait, what do you said about the partial derivative with respect to the x, y and negative 1? So that would be a normal vector?
If I wanted to find the specific formulas for these guys,
Okay.
let's actually do it. We're going to do it anyway, so. So let's just take this example, which was from the quiz. Let's take it a little bit further. So let S be the boundary of the region bounded by z equals x squared plus y squared, and z equals 1, and it's getting hot again. Now, we'll get more practice with this, but how you would deal with this surface is you would literally break it into two parts. You think of this surface as being equal to the union of two surfaces. So you can call this one, for example, S1, and call that one S2. And so you'd find the normal vectors for each one. So if we were to say, for example, find the normal vectors to S so that it is positively oriented. So what you would do is you would first you should have this picture in your head, or you should actually draw it so it looks like that. Where this is the surface 2, that one is given by z equals, let's call this f of xy, x squared plus y squared. This one is surface, which one did I call this surface 1 actually. This one is surface 2, which is z equals, let's call this one g of xy, which is literally the constant function 1. And so for example, there are two normal vectors here. I can talk about the normal vector with respect to surface 1. I can also talk about the normal vector with respect to surface 2. But both of these together will make up the orientation of the whole surface S. So for this one, I can use that formula, minus fx minus fy, positive 1. Now, I know I need to be positively oriented, right? Which means I need the vectors to point like this and that. Meaning on S1, my vectors need to be pointing down, right? So is this the right formula? No, I would take the negative of that. Right? Not just you regurgitating a formula. You'd have to know how to tweak the formula to get what you want. So me saying it's positively oriented, meaning on S1, my normal vector should be pointing down. So I'm going to use the formula where the z component is negative.
Okay.
Right? So if you memorize the formula where the z component is positive, just take the negative of that vector. You'll literally get the guy that's pointing in the opposite direction. And so that would be my formula. And so this would be the positive partial with respect to x, the positive partial with respect to y, and a negative one. So that would be how I can describe all vectors along this bottom part of the surface can be described by this function. So if I want to figure out what is the normal vector right here, right? Well, in the xy plane, it projects down to a point, plugging those x coordinates into this function, and that's going to be your normal vector. For n2, I might just memorize the formula, the partial with g with respect to x, partial with g with respect to y, positive 1. And it turns out I want my vectors to point up, so that's the right one because my z component is positive. So that's going to be my formula. What is the partial with respect to x of this function? 0. 0, 1. And that kind of makes sense because this is a flat surface, right? You expect the normal vector to be pointing directly up and not moving in the x or the y, so that kind of makes sense, right? And of course, with enough practice, when you look at something like this, you'll automatically know that that's the normal vector. You won't have to go through the formula, but I'm just showing you guys here. Okay. So this is the idea of being positively oriented. It's when you describe a closed surface in such a way that all its normal vectors are pointing out. This might mean up, it might mean down, it depends on the surface you're dealing with, what part of the surface you're looking at. And the easiest way to do that is to be able to just sketch the surface, and you'll definitely be able to see, well, this clearly is pointing down, that clearly is pointing up. If you can't sketch the surface, I guess there are ways you could figure it out, but I wouldn't try it. I think it would be a lot harder. It's much easier to just know how to graph the thing and draw it. Good. So there are many cases where we're going to want to take integrals over this surface, in which case the direction of the normals will matter. It will matter. In the case if I'm taking a surface integral over a scalar field, it actually doesn't matter if I get the signs right, because I'm just going to take the magnitude anyway. But there are integrals where I don't take the magnitude. I actually use the vector itself, and the direction of the vector will be important to the answer. Like, it'll have some sort of application. So that was kind of the crash course on oriented surfaces. Okay. Now, I'm going to define a surface integral over a vector field. I can get rid of this, right?
This is the
And we'll talk more about how the right-hand rule affects things here when we get to, well, Stokes' theorem, that will kind of come in handy. I'll talk about the right-hand rule when we get to Stokes' theorem. So let's talk about, what did I say? I'm doing definition. And I'm going to define what the definition is about the surface integrals over vector fields. Which will be different from surface integrals over scalar fields. So suppose we have a vector field F. And the same stuff applies. Like continuous, it behaves nicely. Continuous partial derivatives. And f itself is continuous. F is defined on R3. Then surface integral over F with respect to a smooth surface S is given by double integral. And now this is going to the bonus problem in the quiz. It's F dot product ds. This is the notation for such an integral. I exaggerate the dot here because it's not just multiplication, it's a dot product. This is defined by that guy, right? So notice the definition here takes the unit normal into account, but we know that ds is just the magnitude of the normal times dA. So this really, if I go down to the surface D, where I'm trying to change it back into my rectangular coordinate system, this just becomes F dot product with N dA. Right, and this is since ds is the magnitude of N dA. So this is the formula I'd say you guys should remember. Dot product with N dA. And the N here is given by the formula that we've talked about before. You should also notice we're doing a dot product, which means both of these guys are vectors, which means you're not taking the magnitude of the normal vector, so the direction in which you're pointing will be important. So it's going to depend on an orientation, which it will be given to you somehow. So I'd say positively oriented if my surface is closed, or I can tell you oriented so that normal vectors point up, or they point down, or they point to the right or to the left. Right, so there is going to be some directional component here. The orientation will matter. It's kind of like the analogous to f dot dr versus FDS, right? In one, the orientation didn't matter, but in the other one it did, because the direction will be important to the applications we want to use it on. Yeah.
Can you show us, like if we had a paraboloid z equals x squared plus y squared, how would we say you want the normal vectors all pointing to the left? How would we do that?
Well, we couldn't do that all pointing to the left. I could say all pointing
it's
down.
closed. Okay.
Yeah, I could say something like all pointing down.
So
But
with
the
a
direction in which I say, it's going to be based on how the book draws the axes. So the x is over here, the y is over here, z is over here. So if I'm saying pointing to the right, I mean towards this way. Pointing to the left is towards that way. Pointing down is towards the negative z. Pointing up is towards the positive z.
Would you only do that with a
Otherwise.
plane because that's not a closed
Hmm?
thing? You said planes are not closed, and you would only do right or left or up or down if it's not closed.
Yeah.
So that's when we can expect it?
No, I'll tell you. You'll know based on the question. I mean, when we get to questions where that's going to be important, you'll see it, and we'll talk about it. There are also times when I guess we can mention the. I guess now is as good a time as any. Probably the way to best answer your question is to talk about the right-hand rule. So there are times when we want to define a surface so that its boundary curve is positively oriented. And so, this is for open surfaces. So which would apply to a plane or a part of a disk or something. But again, not all the time. I could say up or down, and it should make sense in context based on the kind of surface I give you. But we can often orient, for open surfaces, we will often orient them so that their boundary curves are positively or negatively oriented. So to give you an example, I can say something like the following. Let S be the part of the paraboloid z equals x squared plus y squared below z equals 1, oriented so that its boundary is positively oriented when viewed from above. Sketch X and its normal vectors. So there's a description. Let's actually work through that. We'll compute some examples of this later on, but it's important that we understand all the details that go into setting it up. Okay, so describe this to me. First of all, you realize the difference between this description and the one on the quiz, right? How one I can think of as a closed surface where this one is not. Can you see why this is a closed surface? An open surface?
So you're only looking at like the cup?
I'm looking at the cup part. I'm not including this part. I'm saying S is the part of this that is below that. Meaning I'm not considering this as a part of my surface. So it's the paraboloid, but there is no top. It's just a part of the paraboloid that's below that level. Okay? So it's actually open. right? So this is open, you can go inside, right? So I'm only talking about the part of that that's below that point. I never said something like S is the boundary of the solid region bounded by this. That's different. Or is comprised of this surface intersected with that surface. That's different, right? From me saying it's the part of this paraboloid that's below that. That's me saying you an open surface. The boundary curve of this surface would be the circle that runs around the ring at the top, right? Now how this is described is that its boundary is positively oriented when viewed from above, meaning if you're looking down, you're seeing a positively oriented curve. And what does that mean?
Counterclockwise?
It means you're running around that curve counterclockwise, which means you need to be running around the curve this way. Now how do you determine the normal vector? Because I had to draw S and its normal vectors. Is the right-hand rule. Now how the right-hand rule goes is that you turn your fingers in the direction that the curve is oriented and you stick your thumb up. And it has to be your right hand, okay? So my fingers are going in that direction and I stick my thumb up, which means my normal vectors need to point up. So the normal vectors on this surface go that way. At any given point, they're pointing inside. Well, if it was closed, they would be pointing inside. Now I could compare this to, for example, z equals 1 minus x squared minus y squared above the xy plane. I could describe that so that's this guy. Again, if I orient that so that the curve is positively oriented when viewed from above, that means I'm running around this way. The right-hand rule would tell me pointing up. So literally, this part of the sentence would not change, and it changes the direction that your normal vector is pointing in, because it depends on the surface that we're looking at, right? So I can literally take this part and swap it in here, change nothing else about the problem, and the directions of my normal vectors will change. So it's very important that's why it's important that for you to know how to draw a surface, what it means to be positively oriented curve, knowing how to look at a region. So if you're viewing from above, you should be able to visualize 3D space. Oh, that means I'm looking down the z-axis and things like that. Anyway, we'll compute some examples next time. It's sort of a lot to swallow at the moment. But all this will go into computing a surface integral over a scalar, over a vector field. We'll do some examples next time.
Professor, did you finish 13.7? No, right?